Okay, next up we have Amy Hanna. Amy Hanna is a senior associate with Hazen and Sawyer in their Raleigh, North Carolina office, where she has been for over 7 years, following 5 years of experience in Ohio. She is a registered professional engineer in North Carolina, Maryland, and Ohio, and earned bachelor's and master's degrees in civil engineering from Case Western Reserve University. Amy's areas of focus are biosolids management and wastewater treatment. Please welcome Amy.
All right, can you guys hear?
Keep it close.
Close, really close, okay. Good afternoon, thanks for having me here today to talk about the WSSC Bioenergy project. We've got a great project team headed up by the commission and also with the program management team with HDR and Brown and Caldwell. I know Stephanie and Chris are here today. And it's been really collaborative and really helpful, as you'll see on some of the next slides, to have real-time cost info to help make some of these decisions during design. So today I'll give you an overview of the bioenergy project and then talk you through some of the decisions that we had to make as we were moving from the basis of design phase, from the design criteria report, into detailed design. So we'll talk about how we selected the tank and cover construction, mixing technology, and the big one is digestion volume and tank configuration. So here's an overview schematic of the process. It's going to be located at the Piscataway plant, and so the indigenous material is kind of depicted on the top row there. So it's going to be thickened across their existing rehabbed gravity thickeners, and then the material will be screened and dewatered on belt filter presses. Then the cake will be mixed with imported sludge from WSSC's 4 other plants. And then that combined material is going to go through THP, digestion, and post-dewatering on belt filter presses. And there's other components to the project as well, gas cleanup and CHP, as well as side stream treatment and utility water. So to give you a sense of the scale of the project, there's about 20 dry tons per day that's going to be coming through the Piscataway stream, and about 50 dry tons are going to be imported. So there's about 70 tons per day going into the THP process, and we'll be taking out about 40 dry tons per day out the back end of the plant. Here you can see a rendering of the 60% design. Let's see here. So in the middle you can see their existing gravity thickeners that we're going to rehab for the indigenous material. So after it's thickened right here, it will be sent back to a new solids building to be screened and pre-dewatered, and the cake will be pumped over to these 2 cake silos. And that's where it's going to be mixed with the imported material that comes in through the receiving facility here. And then it'll go through THP and cooling, and then sent over to the digesters. Then the digested hydrolyzed material will be sent over to the solids building on the post-dewatering side, where it'll be dewatered and conveyed to this cake storage facility. In the foreground, you can see the side stream deammonification process, and in the back is all of the gas cleanup, CHP engines, the boilers, and low-pressure gas storage. And this facility sits right on the Potomac River, which kind of is an issue with regard to its location. So some of these topics, as we were kind of working through, are a little bit chicken and egg in terms of, what thing do you pick first and how does that inform the next decision. But the first thing we're going to talk through today is the tank and cover construction. So we looked at 3 options for tank construction, including cast-in-place concrete, post-tension, and pre-stressed concrete styles. We also looked at fixed steel covers and fixed concrete covers. So first we wanted, this is where you get to the chicken and egg a little bit. So we haven't quite decided how big the tanks are, so we looked at a range of digester sizes. But the height, we were kind of constrained by the height here. So a couple miles down the Potomac River is Mount Vernon, and they have a viewshed restriction in terms of how high we can build on the Piscataway plant site. So that, combined with high groundwater, limited us to a 50-foot sidewall for the digester tanks. So we looked at a range of diameters from 72 foot the whole way up to 81 foot. And we couldn't really go any bigger than that anyway because the site was pretty constrained. So I wanted to just give you a few notes on how the cost for the tankage was developed. We didn't include mixing in the cost because across all the range of sizes, the mixing cost was the same. We got the same proposal for mixing systems. We didn't include any cost for foundations, but we did include the gas appurtenances and wall coating. And that kind of comes into play particularly when we're looking at a 2 or a 3 tank solution. We did include HDPE liners for the concrete covers, however. Okay, so what you can see on this slide is the estimated cost of work for each digester tank in millions of dollars. And you can see there's the range of sizes across the top and then the various construction methods. And what you'll notice is that across all the sizes, the trend carries in terms of the cast-in-place tank with a steel cover was the most expensive for all the sizes. And the pre-stressed tank with a concrete cover was the least expensive across all the sizes. And what you can see here is that the steel cover generally is more expensive than the concrete cover because of all the time it takes to weld it up. But that was not an option, so the concrete cover, which was less expensive, wasn't an option for the post-tension style, which pushed the pre-stressed tank with concrete cover to be the least expensive option. So with that, we made our first decision moving forward that we would use the pre-stressed tank with a concrete cover. So then we wanted to decide what type of mixing we would use, and we looked at draft tube mixing and pump mixing. So with draft tubes, you have higher energy efficiency, but it's going to cost you more upfront, and the inverse is true with the pump mixing. You'll spend less in capital in the beginning of the job, but over time, it is more energy and more energy costs. We found the pump mixing to be more maintenance friendly with all the moving parts and maintenance items at grade outside the tank. And for the draft tubes, we did take into consideration that there would be periodic crane rental for maintenance of the equipment up on top of the tank. So we put together a life cycle cost evaluation over 20 years, and you can see draft tubes versus pump mixing here. So pumped, less expensive on the capital end, but we have almost 30 horsepower additional draw per tank. So, that relates to a little over $300,000 of additional operating expenses, which ended up being more than offset when we took the crane rental into consideration for maintenance. So overall, the higher value solution for WSSC for their digesters was pump mixing, and so that was the technology selected. Okay, the fun one, digestion volume. So for the Bioenergy project, our goal was to hit a 12-day SRT under the peak 14-day loading condition, which was about 176,000 dry pounds per day. And this is kind of a very simplified cartoon of how we wanted to start thinking about all the things that would go into sizing the digesters. We allowed for grit at the bottom as well as mixing inefficiency when we were calculating the active volume of the digester. And then the big one for this, since we have THP, is the rapid volume expansion allowance. So I know most of you guys have sat through dozens of presentations about THP, and you know how the RVE, the rapid volume expansion, is much more of a concern with the hydrolyzed sludge since it's more reactive in the tank. So the big question was, how much RVE do we want to accommodate? So the basis of design was set up around 2 primary digesters and a secondary digester. And there was minimal RVE allowance in the primary digesters, followed by more overflow capability to the secondary digester. And after the basis of design had been published and established, there was continued work by Chris Moline and Matt Higgins. And what that indicated was that the sludge that we were going to have in the Piscataway digesters, which was both from Piscataway and the imported material from the other plants, was actually more viscous than they had seen on other THP projects. So the bottom line shows DC water sludge, and then the red and the blue lines show what they had in the pilot with the WSSC material. So what that led to was an observation of up to 30% volume expansion when mixing was stopped in the pilot digesters. So after discussion with the project team, we decided that we wanted to accommodate up to 30% volume expansion for these digesters. So on the left-hand side, you'll see what was laid out in the design criteria report for digestion. So 2 primary tanks, a secondary digester tank that would serve both for volume expansion and for sludge storage ahead of dewatering. The little orangish brown tank is just a day tank that provides suction going to the post-dewatering feed pumps. So what we wondered is, would there be value in a 2-tank solution? What would that look like? We still need to address digested sludge storage. So a decision was made on this project that they wanted to operate the digesters as constant level digesters, and we're going to have constant feed coming in from the THP process. But they only wanted to dewater on the post-dewatering process 14 hours a day. So we needed to have a wide spot in there for storage. So this is what it ended up looking like once we costed it up. So you can see here the range of tank diameters and how much volume expansion could be accommodated inside the tank with each of those diameters. And at the smaller size, we would need a 3rd tank to be able to accommodate the RVE that we wanted for this project. But with the larger tanks, we were able to eliminate that 3rd digester tank and accommodate most or all of the volume inside the tank. And you can see moving to a 2-tank solution saved about $2.5 million of project construction cost. So what that ended up looking like for this project was a 78-foot diameter digester or 2 78-foot diameter digesters were selected, and they would operate with a normal water surface around 40 feet. The overflow would be set at 49 feet, so you've got almost 9 feet of freeboard before you hit the emergency overflow, and then the top of the digester sidewall is set at 50 feet. So we established that we wanted to accommodate 30% volume expansion, and I just said with the 78-foot diameter digester, we've only got 26% volume expansion in the tank. So where's the rest of the material going to go? So it's going to go in what we affectionately call the bathtub. And here you can see a 3D rendering of the digestion complex. And so you see the 2 digester tanks here, and here's the control building with the mixing and recirculation and withdrawal pumps. And built around it is a 2.5-foot high concrete wall that's at grade, and it extends about 10 feet past the digester walls. And that provides the volume that we need to get to be able to contain up to 30% volume expansion. Another important thing was the commission wanted to be able to contain all of the volume expansion, didn't want any of it to just go uncontrolled on grade. So this shows a little bit better what's going on with the digester. So if the digester experienced expansion beyond 26%, and the sludge started moving into the overflow, it would come out in these locations here. And then the sludge would move around at grade, around the tanks, and this is the location of the 2 outlets to plant drains. So the bathtub is sized to be able to contain that 4%, the additional 4% of the volume expansion, but it does have an open outlet to plant drain. So any material that goes in will flow around and ultimately go out. So as I said, we still needed digested sludge storage to be able to accommodate the intermittent dewatering schedule. And so what was selected was to repurpose the 4th existing gravity thickener for digested sludge storage. And after some different alternatives to improve redundancy of the system, we decided to move the low pressure gas storage off the top of this tank. So originally we had a membrane that we were going to mount to the walls of the existing gravity thickener. So we would have both digested sludge storage and low pressure gas storage. But ultimately we went with a fixed cover for digested sludge storage, and the low pressure gas storage is going to be located remote from that. And it's a bid alternate for this project. So big picture, just some things that I reflected on. You know, it was great to have a collaborative team with a lot of different voices and thoughts and ideas as we were trying to come up with the most reliable, low-cost solution for WSSC, and also having that real-time cost info from PC on our team was very valuable in making all these decisions. So moving forward, the 60% documents are prepared, and soon we'll be submitting the permitting set to MDE and working towards a GMP and start construction next year. Does anybody have any questions? I think that it's viewed as a very low probability event that we would have, you know, take up all 9 feet of freeboard in a tank and then you would have odor. I think it's kind of like a oh crap moment. So no, you know, odor control provisions for that oh crap moment weren't the biggest concern.
I have a question.
Yeah.
From your drawing, I figured that you're considering 95% active volume to be registered because you have 5% for
Grit and mixing, yeah.
Right? That appears to be a available volume, not necessarily an active volume, because you have to take mixing into consideration when you're calculating your active volumes. And those pump mixers, I'm not super familiar with them. I don't know if they offer enough efficiency. Do they even warranty anything along the lines of what active volume those types of mixers should guarantee?
Yeah, so big picture wise, and I only showed the pump of the pump mixing. So there'd be a big centrifugal pump, and then there's a network of pipes that go into a tank with nozzles. And so it's all based off a super high velocity coming out of the nozzle, and they're oriented around the tank and at various levels if they're big enough. Yes, so we're still kind of in the procurement and negotiation stage of all these things, but there are various performance and process guarantees associated with those things. Some of which will be demonstrated in the field in the actual tanks. So.
What are their plans for the end use
Sorry, I couldn't
the
understand.
end use of the material, what do they plan to do with that?
So that's what I was talking to Malcolm about. I don't know if Stephanie has other updated information, but so like DC Water has their Bloom product, and I think that that's something that has to continue to be developed for this project.
Mike.
Oh. Oh, he asked about the end product and what are they going to do with the end product material. I don't know. Is Malcolm in here? I can't see. Ah. What are you going to do with your end product? This great Class A sludge.
I'm going to pyrolyze it, turn it into biochar. We're investing in a long-range biosolids management plan where we'll look at all available alternatives. Yeah, and eat market demand. Big gas talk. It's a work in progress.
Yeah. We got a few years. Yeah, Terry.
What's the redundancy plan if the digester has to be taken out for cleaning?
Yeah, so there was a lot of talk about that, and so what you have to remember about this plant is we are importing over 2x of the material that we have indigenous. So I can't remember the number. I think we can accommodate, 50 dry tons through one tank with 12-day SRT, There was discussion of, so what you do is you don't bring all the material on site, right? Some of it you would divert off if you were in a one tank situation. And then could you push a lower SRT since it's hydrolyzed? Maybe, you know.
So some of it is still the lime stabilization system is going to remain as a backup, or is that going to be just all in the landfill?
So we're not doing anything to the existing dewatering building that has, but the lime is added to the liquid, it's not added to the cake. So I think that the lime, temporary lime, that's a question still. But I think the idea is that they can accommodate all the indigenous and some import through one tank and be okay.
Yeah, they would have to, you know, they would have, the other plants, they would have to do something, maybe not necessarily lime, but they have to find out. So I agree with you. This was basically the decision that, you know, the SEC said, we'll manage this much, you know, another way, if one legislature